Welcome to the debate. In 1890, if you wanted to power a light bulb, you practically needed a power plant in your own backyard.
Literally next door, yeah.
Right, electricity was this highly local luxury. It was entirely bound by the physical limits of copper wire.
Meaning human progress was basically tethered to the exact spot where the energy was created.
Exactly. Yet just 6 years later, humanity figured out how to take the deafening, massive roar of Niagara Falls and silently beam its power 40 kilometers away.
To light up the entire city of Buffalo. It's incredible.
It really is. We are looking at the late 19th century effort to harness the monumental power of Niagara Falls, which is the project that fundamentally birthed the modern electrical power industry.
And the fundamental question we're grappling with today is how to understand the true historical significance of this event.
Right. Where does the real credit belong?
Exactly. Are we looking at a story fundamentally about mechanical generation? You know, the unprecedented taming of raw natural forces at an industrial scale?
Or is it a story about electrical transmission, the pioneering success of overcoming spatial limitations to actually move that energy?
I argue that the defining achievement was the technological leap of alternating current transmission to Buffalo, which conquered the fundamental barrier of distance.
And I contend that the foundational triumph was the sheer physical scale of the 1895 hydroelectric generation. Without that, the transmission and really the entire concept of a modern grid would have been economically and practically impossible.
Well, to understand why I place the emphasis on transmission, we have to look at the exact roadblock of the late 1800s. The central problem of the era wasn't finding energy.
No, of course not. It was moving it. The explicit challenge was how to transmit electricity over long distances efficiently. Before the success at Niagara, the dominant system was Thomas Edison's direct current.
DC power?
Right, and direct current had a fatal flaw. The resistance in the copper wires turned a huge amount of electrical energy into wasted heat over long distances.
Which is a massive problem if you want to power a city.
Exactly. To compensate, you either had to use incredibly thick, expensive copper cables, or you had to build a local power station every mile or so. It was a geographic straitjacket.
Which severely limited industrial growth to very dense urban centers.
That brings us to the visionary alternative, which is Nikola Tesla's alternating current. Supported by George Westinghouse, Tesla believed alternating current was the future, specifically because of its relationship to distance.
Because it could travel miles with vastly less energy loss.
Right. And why? Because of transformers. A transformer can step up the voltage, the electrical pressure basically, before it goes onto the wire, which proportionally drops the current.
And since heat loss in a wire is exponentially tied to the current,
lowering the current means you suddenly eliminate most of the wasted heat. You push it across the wire efficiently and then step it down at the destination so it is safe to use in a home.
It's an elegant solution, I'll give you that.
When the Niagara project successfully transmitted electricity 40 kilometers away to Buffalo in 1896, it proved that this AC transformer framework was practical at a municipal scale. That transmission was the key that unlocked the entire modern electrical power industry.
Okay, but
it wasn't just about water spinning a wheel. It was about the wire that freed us from the water.
I come at it from a different way, because generation fundamentally dictates transmission. You cannot distribute what you haven't successfully captured at scale. But the wire is what makes it useful. Sure, but to say the achievement is about the wire entirely misses the physical, brutal reality of what Niagara Falls is and what engineers had to do to survive it.
Okay, fair point.
We are talking about 3 massive bodies of falling water dropping roughly 50 meters. That's moving millions of liters every single second. The transmission to Buffalo didn't just happen in a vacuum in 1896.
No, it took years of planning.
It was entirely reliant on what happened a year prior in 1895, which was the construction of the Adams Power Plant Transformer House.
But the power plant is just the mechanism to get to the true milestone, which is the transmission.
The plant is the foundational catalyst. The theoretical elegance of a transformer means absolutely nothing if you don't have enough base power to justify the infrastructure.
You need power to move power, obviously.
Exactly. Before you can step up voltage, you need an immense amount of kinetic input. Think about the mechanical achievement required here. They had to dig a massive wheel pit 140 feet deep into solid limestone.
Wow, that deep?
Yes, and they had to channel that falling water down massive steel pipes called penstocks. The pressure at the bottom of a 50-meter column of water is staggering. Standard technology of the time would have simply shattered.
So they had to invent completely new turbines.
Right. The sequential mechanical triumph of scaling up turbines that could withstand that pressure and using them to rotate dynamos the size of houses, that is what actually gave Tesla's system a payload.
Dynamos the size of houses? That's incredible.
You cannot celebrate the distribution of wealth without first acknowledging the creation of it. The sheer scale of the natural energy captured there is the true milestone.
Okay. I have to admit I'm getting a bit hung up on your focus on the physical plant.
How so?
Help me understand something. Weren't there already water wheels and mills all over the world? I mean, people have been using the kinetic energy of falling water to grind wheat and run textile looms for centuries.
Of course.
So why was the Adams power plant mechanically different from, what a miller was doing in Massachusetts in 1850?
That is a crucial distinction. A water wheel on a Massachusetts river might generate a few dozen horsepower. It just sits in the flow of a modest current.
Right, a gentle stream.
But at Niagara, they were dealing with the full force of one of the largest waterfalls on the planet. To handle that, they couldn't just dip a wheel in the water. They had to use these massive Fourneron inverted outward flow turbines.
Okay, that sounds intense.
It was. They had to balance the downward force of the gigantic, incredibly heavy 5,000 horsepower dynamos with the upward thrust of the highly pressurized water rushing through the turbine.
So the water is literally pushing up against the weight of the machine.
Exactly. It was this delicate, high-stakes balance of physics. Westinghouse had to build generators that were roughly 5 times larger than anything that had ever existed. This wasn't just a mill. It was the invention of the centralized mega plant.
I'm not convinced by that line of reasoning because it still views the generation as the end rather than the means.
Well,
let's use a metaphor to clarify the stakes of the era. Think of moving electricity over distance like trying to deliver hundreds of buckets of water by hand over 40 kilometers.
okay, that sounds miserable.
Right. It's exhausting. And through sheer physical friction, or in this case, electrical resistance, you spill most of it along the way. That was Edison's direct current. His solution was basically just to build a new well every few blocks.
Not very efficient.
No. But Tesla and Westinghouse realized that if you could use a transformer to step up the voltage, you were essentially freezing that water into a massive aerodynamic block of ice.
A block of ice?
Yeah, you freeze it, slide it almost frictionlessly across a frozen lake for miles, and then melt it at the exact moment it reached the destination. The alternating current transmission infrastructure was the ice.
I see where you're going with this.
Without it, the massive 5,000 horsepower dynamos at Adams power plant would just mean you had a huge surplus of energy stuck at the edge of a cliff.
I'm sorry, but I just don't buy that. Let me tell you why.
Go ahead.
Sliding the ice is a brilliant conceptual framework, sure. But who freezes the lake? Who pumps the water out of the earth at a scale large enough to create that massive block to begin with?
Well, the power plant does.
Exactly. You are focusing entirely on the elegance of the delivery and completely bypassing the brutal, unprecedented mechanical violence required to harvest the energy.
But the delivery is what made the harvest worthwhile.
The limitation of the late 19th century wasn't just the distance electricity could travel. It was generating enough continuous, cheap power in one centralized location to make a long-distance infrastructure economically viable.
But Tesla's system inherently solved the economic problem by solving the efficiency problem.
How so?
By reducing the heat loss, you didn't have to generate nearly as much power to get the same result at the destination.
It solved the electrical efficiency problem, yes, but the Adams power plant proved that large-scale hydroelectric conversion was viable in the real world.
Right. But again,
Let me finish this thought. If you couldn't build those massive outward flow turbines robust enough to withstand the continuous kinetic assault of millions of liters of water dropping 50 meters, well, then Tesla's beautiful theoretical ice block never materializes.
that is a fair point.
The pressure matters just as much as the pipe. Without the Adams power plants proving we could harvest energy at a monumental scale, the entire concept of centralized power generation collapses, and that is what justifies long-distance transmission grids in the first place.
That's an interesting point, though. I would frame it differently. Because the historical record, the actual source material we are examining, explicitly points to the moment power reached Buffalo as the paradigm shift.
The transmission moment?
Yes. Let's look closely at November 1896. Sending power 40 kilometers away to Buffalo was the first successful long-distance transmission of alternating current at industrial scale in human history.
It was definitely a huge milestone.
The moment they threw the switch to power the Buffalo Street Railway, the world changed. The text explicitly identifies this specific achievement, the transmission, as what marked Tesla as a visionary.
Sure, it proved his theories correct.
Exactly.
Why?
Because before that 40-kilometer leap, electricity was entirely dictated by local constraints. Afterward, it became global infrastructure.
But you can't just ignore
A significance of Niagara isn't just that they built big turbines. It's that Niagara was the ultimate high-stakes testing ground for an infrastructure that would soon span the globe. It allowed cities that had no natural waterfalls to still participate in the modern industrial age.
That's a compelling argument, but have you considered why Buffalo was the target in the first place?
Because it was a major industrial hub?
Buffalo was chosen specifically because of its geographic proximity to the source. Nature dictated the terms of this experiment, not just engineering ambition.
I mean, they had to start somewhere.
The Adams power plant and the subsequent transmission relied entirely on the natural, continuous kinetic energy provided by the unique geography of the US and Canada border. It wasn't a generalized experiment in distance. It was a highly specific response to a geographic anomaly.
Are you saying the transmission was merely a secondary thought? Like entirely subordinate to the geography?
I'm saying you cannot decouple the achievement from the specific geology and hydrology of that location. Buffalo was 40 kilometers away. That was an incredible distance for the time. Absolutely.
Right, unheard of.
But the only reason Buffalo could be electrified was because it happened to sit within striking distance of 3 combined waterfalls moving an ocean of water over a 50-meter cliff.
Nature provided the fuel.
Yes, Tesla's system was brilliant. But at Niagara, it was essentially a parasite on the immense raw power of the Horseshoe, American, and Bridal Veil Falls. The geography was the forcing function.
As quite a way to phrase it, a parasite.
It's true. Without that specific, overwhelming natural setup, nobody is attempting a 40-kilometer transmission in 1896, because nobody would have the capital or the baseline power generation to risk the experiment.
I appreciate the idea that nature was the forcing function. Obviously, you don't build a hydroelectric plant in a desert.
Right.
But let's look at how the mechanics actually serve the outcome. You mentioned the sequence earlier, the physics of balancing the dynamo weight against the upward thrust of the pressurized water.
Yes. The engineering marvel of the turbines.
I don't deny the mechanical elegance or the brute force of that sequence. But if we are evaluating the true catalyst for the modern electrical industry, what fundamentally started the age we live in today, we have to look at what broke the geographic tether.
And I argue that the architecture of that generation, the exact sequence of capturing massive external forces to spin a turbine, to rotate a generator, remains the absolute blueprint for energy creation today.
The blueprint?
Yes, whether you are using falling water, steam from a nuclear reactor, or wind across a plain, you are relying on the exact architecture scaled up at the Adams power plant.
Well, sure, the basic mechanics are the same.
You are capturing kinetic or thermal energy to spin a massive turbine to rotate a magnetic field inside a coil of wire. The scale achieved at Niagara was the catalyst because it proved beyond a shadow of a doubt that we could build centralized megagenerators.
I see why you think that, but let me give you a different perspective on the idea of a blueprint. Yes, a turbine rotating a generator gives you power. But we had smaller versions of that before 1895.
Not at that scale.
No, but Edison had dynamos. What we did not have was the transformer-based framework that allowed electricity to be manipulated, stepped up for travel and stepped down for safety.
That's true.
You say the blueprint of the modern world is the spinning turbine. I say the blueprint of the modern world is the grid itself. The source material clearly links this 1896 transmission achievement to the electrification of cities worldwide.
But the grid needs power.
Of course, but it was the proof that AC power is practical for long distances that mattered. If we only perfected the physical turbines, humanity would have spent the 20th century building our cities in dense clusters right next to massive rivers and waterfalls.
That's a bit of an exaggeration.
Is it? We would be completely at the mercy of kinetic geography. Tesla's transmission technology liberated us from that tether. It allowed a city to be built hundreds of miles away from its power source.
But liberation from the tether still requires the anchor. You say we would be tethered to waterfalls. I say we still are tethered to the centralized generation models that Niagara proved possible.
How so?
Think about the physical realities of the AC system you just described. It can be easily stepped up or down using transformers, right?
Right, that's the whole point.
But stepping up voltage requires a massive, steady initial input. You cannot step up what isn't there. The Adams power plant transformer house wasn't just a building where they plugged in some copper wires.
Obviously not.
It was an unprecedented architectural and mechanical synthesis of the natural environment and human engineering. The sheer engineering audacity required to capture the Great Lakes emptying into Lake Ontario, that is what inaugurated the modern era.
It was audacious, definitely.
You're focusing on the fact that the electricity successfully traveled 40 kilometers. I am focusing on the fact that we had enough centralized surplus energy to push it 40 kilometers in the first place. Without the scale, there is no grid.
And my counter to that is entirely about the legacy and the intellectual focus of the era. When we look back at the 1890s, the primary engineering debate wasn't stated as, how do we build a heavier turbine?
Well, they were definitely debating turbine designs.
Sure, but the explicit defining question of the era, the War of the Currents, was how do we move electricity over long distances efficiently? The competing systems weren't competing water wheel designs.
No, it was DC versus AC.
Exactly. Direct current versus alternating current. Thomas Edison versus Nikola Tesla and George Westinghouse. The battle for the future was fundamentally a battle over transmission.
It was a battle over transmission, yes, but it was fought on a battlefield made of falling water.
That's poetic, but my point stands.
The theoretical superiority of AC over DC was debated in academic halls and corporate boardrooms for years. But theory doesn't light up a city.
True.
Math on a chalkboard doesn't power a streetcar in Buffalo. It took the physical construction of the first large-scale hydroelectric power plant in Niagara in 1895 to decisively end the debate.
Right, by proving the long-distance transmission worked in practice in 1896.
By giving the transmission a sufficient payload to prove itself. The text notes that this project started the modern electrical power industry. The industry isn't just a network of power lines.
No, it's a whole ecosystem.
It's the generation facilities. It's the Hoover Dam. It's the nuclear plants. It's the massive offshore wind farms. It is the centralized infrastructure. Niagara proved that if you harness nature on a previously unimaginable scale, you can fundamentally change the layout of human society. The physics of generating that power was the hardest part of the equation.
I think as we draw this toward a close, it's fascinating how intertwined these two perspectives really are.
They really are two sides of the same coin.
Definitely. When I synthesize my position, I have to stand by the legacy of the transmission. For me, the defining legacy of Niagara Falls is how it served as the ultimate testing ground for Tesla's AC transmission framework.
Understandable.
By utilizing transformers to lower the current and conquer the resistance of the wire over that 40-kilometer distance to Buffalo, it proved definitively that energy could be decoupled from its geographic source. It shifted electricity from a localized direct current luxury to a decentralized alternating current global necessity.
And to summarize my stance, I maintain that the foundational triumph was the 1895 mechanical feat at the Adams power plant. Before you can overcome space, you must capture the power.
Right.
Designing turbines that wouldn't shatter under the immense head pressure of a 50-meter drop, capturing the raw kinetic energy of millions of liters of falling water, and successfully converting it into electrical current at a previously unimaginable scale. All of that was the necessary physical prerequisite for everything that followed.
But perhaps we arrive at a point of convergence here. Because looking closely at the engineering history, neither piece works without the other.
I think we can agree on that.
It is a shared truth, beautifully simplified in the historical record. Niagara Falls provided the immense natural energy, and Nikola Tesla provided the visionary technology.
Exactly. And together they laid the foundation for the modern world. You cannot have a sprawling grid without the massive centralized generation to feed it.
And centralized generation without a grid limits human potential to the immediate vicinity of the plant.
Right. The modern electrical ecosystem requires both immense natural forces and brilliant engineering to function.
It really is a dynamic between capturing natural resources and deploying technological innovation that remains highly relevant today. Whether we are trying to harness wind across a continent or capture solar energy from a desert to power a distant metropolis, we are still wrestling with the exact same variables of generation and transmission posed at Niagara in the 1890s.
Absolutely.
We invite you, the listener, to continue exploring the origins of the electrical age and form your own conclusions. Next time you flip a switch in your home, take a moment to think about what it actually takes to bring that light into your room.
It's more than just magic.
Exactly. Think about whether you are marveling at the quiet, frictionless wire stretching across the miles or the deafening, earth-shaking roar of the turbine spinning at the very beginning of the line.